Welcome to Frank Stajano Explains and to the Algorithms course at the University of Cambridge. In this video, I am proud to introduce you to my favorite data structure, the binary heap. You will learn how to use this amazing data structure to implement a sorting algorithm of optimal asymptotic time complexity, appropriately called Heapsort. Merge sort is great, and we could consider that as the best thing we can do, except that we don't like the fact that it doesn't really sort in place. It wants extra space. So could we do better and have an algorithm that reaches the optimal asymptotic complexity but sorts in place without requiring additional workspace? And this is where I introduce you to my favorite data structure, which is the heap, because it's going to be useful in building an algorithm that has amazing features. So the heap data structure is something that I'm going to show you here. This is a binary tree, but interestingly, it's also a heap. A heap is a binary tree which has two special properties. The first property is called the max-heap property. There exists a max heap and a min heap. I'm going to use the max heap today. At some other point, we'll use min heap. Max, they are symmetric. Max heap property. The max heap property is that the parent is always greater than or equal to the children. And so no child is bigger than its parent. And if you look at this tree, it's the case that for every node, this is bigger than these, this is bigger than these, this is bigger than these, this is bigger than these. That's the max heap property. The second property you need to have in order to call yourself a max heap is called the almost full binary tree shape. Almost full binary tree. Almost full means that the shape of your tree is such that all the levels of the tree have as many nodes as they could possibly have, except possibly the last one. But the last one, if it's incomplete, it has to only be incomplete in its right part with no holes. It has to be filled up from the left and then stop at some point. And if it's filled up all the way, then that's also fine. It's actually full instead of almost full. But you cannot have any empty spaces except at the end of the last level. That's the shape known as the almost full binary tree. If you have that shape, and you also have the fact that for every node, its children don't exceed the value of the node, then you have a max heap. So a max heap is nice for many reasons, and the most important of which for us is that I can easily see where the maximum is. The maximum is clearly, since every node is not smaller than its children, is at the root of the whole tree. So that's the maximum of my tree. Why do I care about knowing where the maximum is? Because imagine this situation. I have already described an algorithm last time where if I look at the array, there's going to be some element that's going to be in the first position that's going to be the smallest of all of them. And if I could find it, I could put in there with just one swap. And the next of what the remaining items, I could take the smallest of them and put in the second position. And I could take the smallest of the remaining ones and put in the third position, and so on. I can do the same with the maximum. I take the biggest of them and I put in the last position. I take the next biggest and I put in the next to last position, and so on. So it's something that in the select sort algorithm was giving me the minimum cost in terms of swaps. Unfortunately, it was still giving me a triangular number of operations overall, because for every position I had to look at all the other positions to find out which one was the minimum of the remaining ones. So this triangular number was a quadratic cost overall. But imagine that I could find the minimum or the maximum of the remaining items, not in linear cost, in how many there are, but less. I know, because I just talked about it, that the optimal cost is n log n. So I have to do the outer loop n times. But if I could find the minimum, or in this case the maximum, in log n, then I could repeat this outer loop with only log n cost for the inner loop, and I would reach my optimal cost of log n. So this is what's happening here, that I'm able to find the maximum every time in just log n. In fact, I can find the maximum in constant time. It's just the top of the tree. But if I take it out of here, I have to reform the heap into a correct heap, and that is the part that costs me log n, so that I can reuse it again for the next time with the remaining items. So if someone says, what's the maximum of the numbers you have? The maximum is 10, okay? Give me 10 because I need to put it in its place at the end of the array. So I get an array somewhere here. And what was the maximum? It was 10. Okay, right. Give me 10. I'll put it here. Now what I have is no longer a heap because it's not even a binary tree. Never mind having these other properties. So the first thing I need to do is reform it as a binary tree. I have plenty more things that could go here. Would it be a good idea to put this one here, for example? It's pretty big. Actually, no. Because if I do that, I leave a hole somewhere else. So and then I have to start filling this up in some other way. So the only thing that will comply with the tree keeping this shape of almost full is if I remove something from here. The last element here is the one that will keep the shape. Now I fixed it one side and I've broken it the other side because now it doesn't comply with the max-heap property. But at least I'm keeping the shape. So if I keep the shape, let's say, let's have the shape first and then worry about the max-heap property next. Then if I worry about the max-heap property, this one should be something that is at least as big as its children, but it's clearly not because this one is bigger. So if this one is bigger, let me just promote it instead of this one. If it was the bigger of the two children, then it's also bigger than this one, so this one doesn't have to worry. And this one, because it was all right before I removed the 10 originally from this position, then the heap rooted here is still a heap rooted here, and I haven't touched it, so I can just continue not to worry about it. Now this one, I've put this 2 instead of 8. 8 was good as the root of a heap in this position. Is 2 good as the root of a heap in this position? No, it's not, for the same reason that it wasn't at the top, because this one and this one are both bigger. So I take the biggest of them, and I swap it here. And then I check again in this subtree. Well, this subtree is orphan of one side. And I have to keep doing that in this case, going all the way to the bottom. So to satisfy the shape of almost full binary tree, I take the last element of the tree and I stick it at the top. But then to satisfy the max-heap property, I may have to send it down until it reaches its natural position. Now in this case, 2 was the minimum of the whole tree, and therefore it had to go all the way down to the bottom. But if it had been a bigger value, it might have found its place somewhere earlier, and it might not have needed to go all the way to the bottom. But in any case, the worst thing that can happen to the value I insert here is that it travels all the way to the bottom of the tree. I only do things that go down one single path. I never have to worry about more than one path because the part I don't touch stays fine as it was. It was a heap before, it still is a heap because I haven't affected its root. So the longest path I can have in a tree like this is the height of the tree, and because the tree is very well balanced as it can be for the number of nodes it has, thanks to the almost full binary tree shape property, then its length of its longest path is bounded by the ceiling of the logarithm of the number of leaves, of the number of nodes it contains, which is the number of items in the array I'm trying to sort. So this bound, logarithmic bound on the height of the tree, is a logarithmic bound on the cost of fixing up the tree, because I have constant number of pointer changes per level and the maximum level bounded by the height, which is bounded by the log of n. And so extracting the identifying the maximum is constant cost, extracting it and reforming the heap is log n cost. And so I can repeat this step for each of the n positions in the array every time, paying no more than log n. In fact, this is log n, is less than log n, because every time I do it, the n is actually smaller. It's not the original n. But never mind, it's definitely bounded by log n of the original n, and so I can merrily go around and finish sorting this in n log n total. So my next maximum of the rest would be this, and I'd have to promote the 2 here, and then it would have to go down somewhere again in order to reform the heap. And then the next time, when I extract the 7, the one I take out is this 4, and I'd have to put it back in and do the same. So this is very good, because it means I have now managed to sort my original array in n log n, but the smartest among you will say, you did all this because you complained that poor merge sort was poo-pooed for having extra storage. And now you're using an extra tree, so how's that any better? So surely a tree is even worse than the extra storage that you were using for merge sort. And I say, well, let me try and be economical about this tree. This tree, how much store, I mean, trees have pointers to the parent, to the children, and all that kind of rubbish. So it's conceivable that the tree might use up more space than just the space to hold the payload of its nodes. However, I'm going to use a trick. My trick is exploiting the fact that the shape of this tree is that of an almost full binary tree. So I know that all the levels of this tree are full with nodes for as long as there are nodes, and then at some point stop, and there's nothing else after that. So why don't I linearize this tree by going level by level? So I first take this, then I take these, then I take these in this order. So I'm going to call this position 0, this position 1, this position 2, position 3, 4, 5, 6, 7, 8, 9, 10, and so forth. So when I want to transfer my tree into an array, another array, what I do is simply, well, let's start with one that's actually a proper heap. I put this one here. I put this one here, and then I put this 1, 2, 3, 3, 4, 5, 6, and so on. There is a direct mapping between the tree and this array. And if I need from the array to make the tree, it's easy. I just start from first one in the first level, next in the next level, next over here. There's no ambiguity about where anything goes. And so I can store my tree in an array without paying any extra for pointers or any other housekeeping junk, because there's this direct mapping between positions in the array and positions in the almost full binary tree. In fact, I can also directly say where are the children of any node. So the children of this one are here. And the children of this one are here. And the children of this one are here. Well, I'm looking them up in here and say, well, the children of this, which is in position 2, are position 5 and 6. So they are here and here. But if I wanted to do it algebraically, what would I do? I would say that the children of something in position I, okay, children of I are at 2i plus 1 and 2i plus 2. So the children of position 2 are in position 4 plus 1 and 4 plus 2. the children of position 4 are in position 8 plus 1 and 8 plus 2. And you can reverse this, this equation to get the parent of any given child. So in constant cost, you can figure out where your children are, where your parent is. So my temporary space for building up the heap is not that expensive. It just uses up exactly as much space as the payloads. So it's not as bad as you thought. But then objection comes back and says, but you still have some extra space that you're using. You wanted to do something better than merge sort, which was not sorting in place. This is still not in the array. And I say, but now that I've made it into an array, I can actually stick it in the empty space here. So I can do it in place, because all these things can fit. That's the rest of the things I haven't put where they belong. I can actually leave them in the original array in here. It's a bit crammed, but OK. And so then I have some kind of boundary that says this is the part, this arrow. To the right of this arrow is things that I've already put in the correct place. And to the left is a max heap that I'm going to extract things from. So next time I'm going to extract something from the max heap. I always extract the root. That's the root of the max heap. I extract it, and where do I put it? Well, is it a problem? No, it's not a problem. No problem, guys, because I always take the thing from the end, which is this one, which exactly makes a space for me to put this where it belongs. Then this thing moves here, and all I have to do is put this here and make it go down to where it should be, because this one has two children that are bigger, so it should actually go where the 6 was, which was over here. And so, so this one should take the place of the 6. And then the 4, which is now here, should see, what about my other two children? I lost count of where they are, but if there's anything bigger than a 4, and I don't think there is, then it should go further down. But because there isn't, then it's fine where it is. And so this is now a heap, and I'm great, and I can just do the next position, extract the 6, and put it there. Right? So this is brilliant, because I am now not only completing the operation in n log n, but I am also not using any extra auxiliary space. I'm doing everything in place without the extra n over 2 space that we were using last time for merge sort. So this is a definite improvement now. Same asymptotic cost and lower space cost and in place. And plus the heap is cool.